Now that we know what a process is and how to create processes, let's see how we do interesting things with processes. I'm talking about this fork exec model, and as we saw before, fork creates a copy of the current process, the process that called fork, and exec v, what's going to do is going to replace the current process code and address space with the code for a different program. Okay? In fact, there's a whole family of exec calls. I encourage you to explore them. Okay? So, for example, here in this code, we are calling fork. So if the PID is not 0, that's the parent. It created a child. Okay? And otherwise, if the PID is 0, that's the child. Okay? And when we call exec v here, the child is going to replace its code and its data and its address space with the code and address space from a different program. And this line here is going to be printed by the parent only, and we'll see. And that's because exec v is not going to return. So let's see an animation of how this happens. Okay, so this is the parent process right here, parent process. Okay, so and when you say that's the bash process, right? The shell that you type in your that you might be probably running in your system. Okay, when you type ls, for example, what's going to do is bash is going to fork, right? Because it needs to create a new process to execute the command ls. Okay, and here's how it's going to happen. So bash calls fork. Okay, so that's the parent, that's the original process here. And now it's going to create a child that at that point is exactly the same. These two are the same. Okay. But now what it needs to do, it needs to call exec and replace what was there in the child with the stack, the address space, and the code for the program ls that's going to list the directory. Okay, so that's a high-level view. Okay, so the bash, which is also a process, happens to be your shell. When you type ls, it's going to create a new process, and it's going to replace the child process with the code and address space for ls, because ls is just a program. Okay, so now here's how exec v works in more detail. That's the prototype of the function. Okay, it receives three parameters. Okay, one is a file name. That's a file name of the executable containing the program that we want to exec. These are the arguments that you're going to pass to the program. And this env is the environment, the list of environment variables. Things like, for example, the current directory and so on. Now note that exec v does not return. Why is that? Well, because it's going to be executing a different program now. And the exec v call was part of the original program that was it's part of the program that was running that was running before exec v. So as soon as you do exec v, that current program is no longer running. That's why it doesn't return. Unless there's an error, then it's going to return. Okay? And as I said before, it overrides the code, the data, and the stack. Okay? It keeps the process ID, open files, and a few other items. Okay? Now, let's see how this collection of data structures here look like in memory. Okay, so that's a stack frame for main. Now we have what? We have the argument count, the vector of arguments. Okay, that's why it points to a list of, it points to a vector, and each entry in this vector is a pointer to the strings with the command line arguments. Okay, now the environment env points to another vector that's a list of pointers to the contents of the environment variables. Okay, so it's a pretty beefy data structure. Okay. All right. So this is how exec v works. Now, how do we end the process? We're going to use a call called exit, and he receives as a parameter a status of why the process exit. Okay. So status code 0 is normally used for normal exits, and non-zero is a normal exit, like there was an exception or there was something happened to the process. Okay. So and if you want to register a function to be executed when you exit a process, you can call at exit because something is going to be executed at exit. For example, say that you call cleanup here, So if you say at exit cleanup, when the process here exits, it's going to call this function cleanup here. Okay? So, but once this happens, it doesn't really completely destroy the process. It creates what we call a zombie process. Okay, so and the reason we call it a zombie is because when a process terminates, it still consumes resources. Okay? So things like many tables in the OS that keep track of processes and so on. So we call it a zombie because it's kind of like a living corpse, half alive and half dead. But what happens if they build up? Well, there's a process called reaping that cleans up after a dead process. And this is performed by the parent process on a terminated child. Okay, so when a parent process creates a child process and the child process exits, dies, the parent is given its exit status information, and with the reaping process tells the kernel to discard whatever was left from the process and recycle those resources. Okay? Now, what if a parent doesn't reap? Well, that could be a problem if the parent runs for a long time. But if any parent terminates without reaping, then the child will be reaped by init process, by the init process. And by the way, the init process is a process that is the parent of all processes in your system. Okay, when your operating system boots and it's ready to execute something, it creates this init process, which is sort of like the canonical process from which all other processes derive. Okay, so and if a parent terminates without reaping a child, then the child will be reaped by the init process. Okay, but one thing to note is that if you have a long-running process, you need to do explicit reaping, otherwise nobody's going to reap it. It's going to be using resources. Eventually, it's going to exhaust its resources. And examples of long-lived processes that need to do reaping are things like shells and servers and so on. Okay. All right. So now that we know what happens when a process dies, let's see how we use that for synchronization. There's this function called wait that's used to synchronize with children processes. Okay. So what it does is when you call wait, it suspends the current process, for example, the parent, until one of its children terminates. Okay? And the return value is the PID of the child process that terminated, because a parent could have multiple child that it's waiting to die on. And on successful return, the child process is then reaped. Okay? And by the way, if the child status is set to not, this is a parameter to the wait function, if it's set to not null, then the integer that it points to, because notice that it's an integer pointer, the thing that it points to will be set to a status indicating why the child process terminated. Okay? So, because now we can read the exit status of the process. This int return here just returns the PID. That's the PID. Okay? And this points to the status at exit that the child had. Okay? So, and there are special macros for this to interpret this status, and you can see wait to, you can do man, wait to, and see what those mean. So now note that if a parent process multiple children, if you call wait, it will return the when any of the children terminates. That's why there's another call called wait PID. And what it does, you can wait on a specific child process by passing its PID as a parameter. Okay, so let's see an example of wait here. So we have this function here called fork wait. It forks here. If it's 0, again it's the child. It says hello from child. Otherwise, that's the parent. That's and it's going to do the following. It's going to do child PID. It's going to do wait on the child and child status, just an integer here. Okay, and when that returns, it's because the child has died. So now, when that happens, it's going to print the PID of the child. Note that this is returned by wait. Okay, and it's going to say it has terminated. Okay, and then it's going to say bye. So let's see how this works here. Here you have originally the process was running, then it forks. Okay. Then eventually the child is going to say bye. Whenever the child says bye, it's because he has returned. Therefore, we come back here, and then the parent calls bye. Pretty interesting, right? Super simple, and in fact, you can imagine very complicated trees and arrangements of how parents and child synchronize. So to summarize, recall that fork gets 2 copies of the same process, okay? But fork returns different values to the 2 processes. And fork is a special function you call once, but we return twice, because that's the point where it replicates the process. Okay? So exec v has a new process replaces itself with the one that called it. Okay? So it's a 2-process program. Okay? So when you call fork, so here's an example of a 2-process program. You first call fork, and if the PID is 0, that's the child code. Otherwise, you exit the parent code, and that's where you'd use, and in the child code, that's where you call execv to replace itself with a new program. Okay, so now at that point you have two completely different programs. Okay, great. So and wait PID is used to synchronize parent and child execution, and whenever you do the synchronization process, the child, like the remains of the child process, is collected when it exits. Okay. So in the final summary of this section, we're now ending our section on processes. So the thing to keep in mind is that at any given time, the system has a lot of active processes. In fact, if you type in Linux ps, for example, -ef to make it return here, to make it easy to read, when you type that, you're going to see the list of all processes running. Okay, so that's your prompt here. You type ps -f, you're going to get a list. Okay? But if you have a single CPU, only one can execute at a time. And the process has the illusion that it has full control of the CPU. That's pretty cool, right? It's a really important abstraction, right? Okay? And from time to time, DOS has to do the context switch, because if there's a single CPU, you want to give the illusion that things are running at the same time. So it keeps bouncing back and forth between the running processes. Okay? So, and we do process management with this fork exec model that you just learned. That concludes our section. See you soon.